This is graph. This is not the graph we talk about in graph theory. We are talking about something that looks like this. A and B have some relation, and then B and D have no relations. So these are the graph. So what is graph? Graph is about connectivity, relation. How do we describe a graph? We draw a picture, or we use set, or we use combinatorics, or too bad, this course now we don't talk about linear algebra, so this part will be gone. I mean, anything related to linear algebra, I assume you don't know. I assume you don't know what is vector. I assume you don't know what is matrix. Don't worry. This thing I said is very hard. No panic. We just touch the basic. So these are examples of graph. This metro in London is a graph. Traffic network is a graph. What the heck is this? This is some quantum bullshit. Is also a graph. What the heck is this? Chemistry is a graph. What the heck is this? Biology is a graph. Electric circuits is a graph. This thing is a graph. Two pictures of horses, I link them, is a graph. This thing is also a graph. This is my academic tree. This is me, and then on top is my PhD supervisor, and then on top is my PhD supervisor square, and then go on top, and you see some big name, blah blah blah, and then in the end go to some name that I don't know how to pronounce. Okay, so this is a graph, and this graph are all belong to something called graph theory. What is graph theory? Graph theory study relationship, and everything has a relationship. Therefore, graph theory is everything. Graph theory is a language to describe relation, and that's why it's very important. The first slide, in slide 4, I'm showing you one of the hardest problems in graph theory is this thing. I'm telling you, these three graphs are the same thing. They don't look like the same. But now I'm telling you, they are the same thing. So in mathematics, we don't say A and B are the same thing. We call them isomorphic. It's just a fancy name of saying they are the same thing, okay? Now I'm telling you, they are isomorphic. That means what? That means there's a function f that is a bijection. I can map 1 to a point here. I can map 2 to a point here. I can map 3 to a point here. Vice versa. I can map C to a point here. I can map B to a point here. And there's a 1-1 correspondent. Then they are the same thing. They don't look the same. We don't care. We don't care how we name the vertex. This is called vertex. 1, 2, 3, 4, 5, 6 are called label or name of the node. A, B, C, D, F, and here W, X, Y, Z. They are, I said, these three graphs start with letter G, so I call it G1, G2, G3. They are the same graph. Although they draw differently, but now I'm telling you they're the same thing. Because of that, what does it mean? It means we don't care about how we name the vertex. We also don't care how we draw it. We care about how they connect. So graph is basically about connectivity. And let me tell you, checking whether two graphs is the same is a very difficult problem and it's still open. That means nobody knows how to solve it. You may think that, oh, I can just brute force doing this. Yes, but for graph, the combinatorics, all the numbers very quickly blow up to some number that is so big that you don't know how to describe it. In other words, the complexity of graph grows up even bigger than exponential number. And that means what? That means telling two graphs, let's say I have 2,000 nodes. Is this G1 and G2 the same? We don't know. And if you want to use a computer to solve it, it will be some, let's say 2,000 power 2,000 and then power 2,000 and then power 2,000. And you cannot even solve it by computer. That means what? It's a very difficult problem. So what is the fancy name of graph? If you want to talk to your mom or your dad, you can say, today I learned something called one-dimensional closed finite weak topology complex. Yes. Graph is something called topology. What is topology? A donut and a cup is the same thing. You can deform a donut, become a cup, and a cup become a donut. What is graph? Graph is something like a donut, with a hole inside, and you can deform the graph and get this kind of thing. And then you can deform this graph to get this kind of thing. So it's the same idea. A donut and a cup is the same thing. So this is just a fancy name. What you need to know is what's graph. Graph have three things, G, V, E. And just a warning, graph is very hard. But I said no panic. We are just touching the basic. My job is to let you understand what's graph. And that's it. Let's start. So what is a graph? The first thing is, why should one study graph? So this is called Maxwell problem. In, let's say, lecture 1, I said, you have a bunch of people want to travel to some city, and then you have a bunch of destinations, let's say Tokyo, Singapore, and then what? And you also have a bunch of people, whether that person can drive or cannot drive. Now you have a bunch of information, and then now a trip is defined as 4 people go to the same location, and at least one of them can drive. How do you solve this kind of problem? This kind of problem actually is a graph problem. And actually you can solve it by something called max flow. And now I'm going to tell you some example of why graph is useful. So for example, let's say you are here, and let's say this is your home, and these are all the possible ways you travel from here to your home. This number, let's say, is the distance or amount of time or amount of money you need to spend if you go from here to here. So what is the problem? Find the shortest path from here to the sink. Sort and sink. A lot of problems in the world can be solved like this. So this is why graph is very important. And now let me give you another example. You have a phone, And sometimes you take selfie, and then suddenly somebody on the back, you want to remove that person. How is that possible? Let me tell you how is that possible. A picture, if you zoom in, there are a bunch of boxes. Okay? So basically, a picture is just a bunch of boxes with different number. You can think of color, it's just number. A picture is just a bunch of boxes. This is called a matrix. Let's say I want to remove the background. So first, as I told you, a photo is just a bunch of boxes. So this is an analogy. I'm not saying these two images are the same, but this means a photo is a bunch of boxes. A bunch of boxes, you can think of all the boxes is a nook. And then what? These are a graph. What is a graph? A graph means a bunch of lines joining different nooks or vertices. So what is separating the baby from the sky? It is you want to have this graph. What does it mean? It means if you look at this graph, this grid never touch the baby. And then the graph, the connection inside the baby do not touch the sky. So you have split this graph into two parts. And then I can say, okay, this part belongs to the foreground. And this part belongs to the background. Then you can get something that looks like this. So white color means belong to type 1, black color belongs to type 2. Then you can now separate the photo. And then you can now do this kind of thing. Okay, this is just an example. Okay, I'm not saying, for example, you can even just chop the head. Okay. And then you may see, some things like fourth eigenvector, third eigenvector. Okay, we don't talk about linear algebra, so that's why I don't talk about it too much. But basically, I'm telling you, the connectivity of a photo is something hidden in the background, is the eigenvalue of the something called Laplacian matrix. I'll talk about it a little bit later, but not our focus. So let me go back. So this is called image segmentation. Let's say you take a selfie somewhere, and then somebody in the background do photo bomb. And then you say, I don't like this person in my background. I want to Photoshop cut it away. So what does the Photoshop cut it away doing? It's actually the thing I told you. You draw a graph on your photo, and then you try to split the graph into two parts. The foreground, another part belongs to the background. And that's it. This is called image segmentation. So this part is basically the basic graph concept, because I assume all of you don't know what the heck is graph in the past. So now this is totally new to you. So what is a graph? Graph have three things. We call a graph G. The thing in G is VE. What's VE? V is called vertex E. It's a set. And we have an edge set called E. Vertices start with V, so we call it V. Edge start with E, so we call it E. Some people call it nook. Some people call it point. And for edge, some people call it curve, some people call it line, some people call it arc. Just name. Okay, I will always call V and E. So, for example, I have a graph that looks like this. I have 1, 2, 3, 4, 5, 6. So all the circle is at a vertex, and I give them a name. 1, 2, 3, 4, 5, 6. So my V set is 1, 2, 3, 4, 5, 6. First thing, we don't care about how we label the nooks. So this is just one particular way of labeling this. I can say this 5 is the 1, and this 1 is a 5. I can do that, because how they connect do not change. So V is like labeling. Then what is 2 bar? You remember 2 bar means the cardinality of set. So in this case we have 6 nook. So V is 6. The size is 6. And what is E? E is edge. E is a pair. It's an ordered pair. We have IJ in V. That means for all the I in V, if I connect to J, I put it in E. So for example, look at this picture. 1 connect to 1. So 1, 1 is in E. 1 go to 2. So 1, 2 is in E. This 1, 2 means from 1 to 2. Okay, this 4, 1 means from 4 to 1. This 5, 4 means from 5 to 4. And if you look at this picture, you will see that 5, 3 appear 2 times. So 5, 3, and 5, 3. Okay, we run out of symbol, then we add subscript AB. This is a graph. So that means what? What is V? V is how many nodes? 1, 2, 3, 4, 5, 6. What is E? All the connection. So 1, 1, 1, 2, 1, 3, 1, 5, 3, 4, 4, 1, blah, 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 and so on. And how many bracket inside means how many edges we have. So there are 10 lines. So in other words, this picture, we now no longer draw this picture. We say this V and this E, we mean this picture. You need practice. There will be some exercise. I give you some V and E without telling you the picture, draw the picture. Or vice versa, I give you a picture and draw the V and E. We will do this exercise together later, okay? And then what is M? Well, this part we call VVEEMAD. So V means vertices edge, vertice, E means edge. The second V means how many V in the V, that means 6. The second E means how many H, that means 10. Then we still have 3 things, MAD. M is incident, A is adjacency, D is degree. Oh, what the heck? So let's look at it. M means what? If I go to J, it's not in E. If I go to J, yes, then you put a 1. If I go to J 2 times, you put a 2. That means what is M? How many times I go to J? That's it. So, for example, how many times 1 go to 2? 1 time. So 1, 2, this arrow correspond to this number, in a matrix. So this M is called an incidence matrix. Okay, but we don't talk about linear algebra, so you should look at linked list. So 1 go to 2. These 4 red things, 1, 2, 3, 4 are the same thing. That means you have 4 ways to represent the same idea. 1 go to 2. Okay? Then what about 5, 3? 5 go to 3 2 times. 1 time and 2 times. Then what? Then you draw it like this, or you put a 2 here, or you put a 2 here, or you put a 2 of them here. So it's the same. So what does M mean? M means incident matrix. Then you may wonder, why don't we use I? Well, usually Ij will be used to denote the node, so we don't call it I. And also in matrix, I stand for identity matrix. Then you may wonder, why? Then what's next? Well, we will use M. M is, that's it. Of course, you don't need to really worry about the naming. We don't care, okay? So M is a what? It's a list. It's a matrix of size V times V. Why? How many columns here? Exactly how many nodes here? How many rows here? Exactly how many nodes here? So these are basically telling you is Ij interact with each other. So this is a V by V matrix. Okay? And this is called an incidence matrix. This is called incident list. So what's the difference? Well, this one basically is the math. This one is the code. So it's the same thing. Okay? Linked list, not yet or yet? Not yet. Okay, then ignore what is list. Okay. Then what about A? Okay, VVEEMAD. What then? A. A stands for adjacency. M is incident. That means from I to J. A means is I next to J. Next to J means I don't care I go to there or they come here. So for example, 1 go to 2, right? Therefore, 1, 2 are adjacent. We don't care about is 1 go to 2 or 2 go to 1. We don't care about which go to which. It's the same as M. M have a direction. A have no direction. So 5 go to 3 2 times, same, we have a 2 here. But because now we don't care about direction, so 3 also go to 5 2 times. So we have a 2. So we have an A matrix. In linear algebra, we'll call this matrix equal to E transpose. That means it's symmetric. It means you have a diagonal here and you flip it, it's a symmetric. And what about the adjacency list? You store all the possible adjacent nodes. So how many guys connect to 1? 1 connect to itself, so 1 1. 1 connect to 2, 1 2. Right? 1 connect to 3, connect to 4, connect to 5. I don't care about the arrow. So 1 connect to 1, 2, 3, 4, 5. That's it. What about 6? Nobody touch 6. So 6 is alone. This means this list have nothing. In linear algebra term, this matrix is all 0 and all 0 here. VVE, right? So this matrix is V by V. What about this matrix? It's also V by V. Then what about this adjacency list? Well, how many number do we need to store? We need to store this number of nodes, right? So V. How many things we need to store here? It will be number of edges. Actually 2 times because we don't care about I go to J and J go to I. So there should be an E. So there be a 2 here. This big O notation means we don't care about constant. So this thing scale along with the size of node and along with the size of E. Okay? Ignore this for a moment. So this is the thing. Then what about this one? You have V and V here. So the complexity. That means how many space you need is exactly how many nodes square. Searching this is very simple. You just go to this particular box. So that cost is called O1. O1 means constant. Technically, it's not O1, it's O some number. But we assume we don't care about the scaling factor, so we always remove the scaling factor. Okay. And then lastly, let me go back. VVEMAD. V means vertices. Second V means how many nodes. E means what is the edge. Second E means how many edge. M means which I go to which J. A means we also is M, but we don't care about the direction. D means how many guys touching the point. How many things go out from 1? So you count how many arrows. 1 arrow go out, 2nd arrow go out, 3rd arrow go out, 4th arrow go out. So degree out is 4. How many guys touch 6? Nothing. 0. How many guys go out from 6? No. How many guys go into 6? No. So 0 and 0. What is this 2? This in means 2 guys go into 1. So which corresponds to this arrow and this arrow. This arrow is going from 1. Okay? So basically what? M means, a 1 means I go to J. For A 1 means I touch J. We don't care about direction. The 2 means touch more than 1 time. 0 means don't touch. What about D? D means how many times this particular node touch other point or go out or go in. Okay, so D in means how many other people go to this node. D out means how many times this node go out. And without in and out, that means how many times it touch. So this is a MAD. And that's it. Basically, if you master this thing, you have already finished the whole graph theory part. I'm not going to go deeper than this. That's it. So, first graph theory theorem called handshaking lemma. Actually, this is something related to pigeonhole principle. I said in a party of, let's say, 20 people, and they shake hands with each other, there will be always 2 of them shaking the same number of hands. So, any graph G, that means I don't care how I draw a graph, any graph with this number of edges and this number of vertices, then the degree of all vertices must be 2 times edge, which makes sense, right? That means what? What's the degree? Degree means how many times the node touch each other. Since this D do not care about direction, so 1 touch 2, we will also count 2 touch 1. And degree means how many times they touch each other. Of course, it will be for what? For each node I, we have a degree, right? How many edges here? We count how many lines. So for example, I have this line. For degree, we will say 1 touch 2 and 2 touch 1. So we multiply 2. So totally number of lines times 2 will be all the degree. So this basically is sum of degree of all vertices. So this means what? This means degree of node I. So if I say degree 5, that means what? How many guys touching 5 or being touched by 5? So that means I'm talking about this number and this number. So this means 1 other node go to 5. This means 5 go to 3 other nodes. Very important. This number saying 5 go to somewhere else, it can go back to 5. For example, this 4, this is the first go out, this is the second go out, this is the third go out, this is also the fourth go out, but in the end it go back. Okay, so this is going out. Nobody said you cannot go back to yourself, okay? Same. So, okay, so make sure you. And then the proof is just one sentence. Nothing fancy, okay? And then another funny theorem. All graph, always, this is true, even number of odd vertices. Odd vertices is called if the degree is odd. So let's go back to this figure. This is odd number, this is odd number, and this is even, this is even, this is even, this is even. Okay? How many odd vertices in this graph? 2. 2 is even. This is true. And how do you prove this? You do this what? First, we have handshaking lemma, exactly this sentence. Then what? This summation means all the vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Some of them are odd, some of them are even, right? So I can split it like this. Okay, so I have this. And then what? I put this even part, I go to other part, so I subtract it, so I get this thing. And then what? This guy, what does this mean? This means all the degree here are even number. 2 times something is an even number. Minus some even number is an even number. This bunch of things is a bunch of odd number. So, that means what? That means I need to make sure this guy is even number. Otherwise, this equation does not hold. That's the proof. Okay, this kind of proof is very not trivial for the first time. So, I'm not going to test you this kind of proof in the exam. Don't worry. So, I just let you know this kind of thing exists. And then, now we go back to the graph. We usually don't care about isolated nodes. So, we have a 6. 6 don't touch other, and other don't touch 6. So, it's the same as we don't care about it. Vertex 6, isolated. We call it isolated. Have degree 0. Degree 0 means nobody touch it and it touch nobody. Then that means also no edge, so we can just ignore it. You have no interaction. As I said, what is graph? Graph is talking about interaction between two nodes. If 6 have no interaction, that means it's not about interaction. Then we can ignore 6. If I have a graph that all vertices are isolated, it's called a null graph. For example, let's say I have a graph G with 3 nodes. 1, 2, 3. I call it 1, 2, 3. Okay? And if these 3 nodes do not touch each other, it's just 3 nodes. This is called nothing. This is like empty set. We call it null graph. But for graph, we have more than one empty set. Empty set is like nothing, right? But I can say I have an empty set in graph with 4 nodes. I can have an empty set in graph for 2,000 nodes, 2 trillion nodes. They don't touch each other. And null start with n, so we call it just n. Okay? And then directed graph and undirected graph. What the heck is this? Directed graph means we have error. Undirected graph means we don't have error. This is a directed graph, and mathematicians are super lazy. They don't want to spell anything. They just call digraph. And then undirected graph, they call it undigraph. So we call this digraph, and we call it undigraph. I have to say this. We have a lot of them because this is totally new for you. So you have to know a lot of them in the beginning. So what is a pseudo graph? We can have loop. We can have more than one edge called multi-edge. Multi-graph means no loop but have multi-edge. We most likely will focus on simple graph. Simples mean what? Here are 3 examples. This is a pseudo graph. Why? Because 1 go to 1. We have a loop. This is a multi-graph. There is no loop. But 5, 3 touch 2 times. Why we don't want to see this? Because when we talk about 5, 3, then we have ambiguity. We don't know whether or not we are talking about this one, or we don't know whether or not we talk about this one. So for simple graph, we will just say that we don't talk about loop, and we only consider one line. So these two are just one. So this is the idea. And actually, we will focus mostly on simple undiagrammed graph. That means even no arrow, okay? Okay, now exercise. Draw this graph. We have a graph G, V, E. V is 1, 2, 3, 4. Again, there's no rule saying that how we should draw the graph. So I draw 1 here, I draw 2 here, I draw 3 here, I draw 4 here. This is okay. I draw 1, 2, 3, 4 like this. This is okay. I draw 1, 2, 3, 4 like this. This is also okay. Nobody care, okay? Because of space, I will draw 1, 2, 3, 4. Okay? 1, 2, right? 1, 2. 2, 3, right? 2, 3. 2, 4, right? 2, 4. Done. Nobody said this line had to be straight line. I can draw like this, okay? So this is the graph. So this graph is GVE. That's it. Next, we have GVE. 1, 2, 3, 4, 5. Okay. Then what? 1, 2. Okay. 2, 3. 3, 1. 4, 5. Okay. I have this. So this is how I draw. Okay. Let me draw another way. So 1, 2, 3, 4, 5. So 1, 2, 2, 3, 3, 1. Okay. And 4, 5. Yeah. These two graphs are the same graph. Okay. Lastly, this one. I have 1, 2, 3. Okay. 1, 2, 3. H that is null, nothing, done. This is a null graph. Of course, make it better, you should always draw circle, but okay, lazy. Now, another example. Find the GVE of this kind of simple picture. Okay. Again, there's no unique label. You can label it as anywhere as you want. So I will call it 1, 2, 3, 4. Then in this case, what is V? 1, 2, 3, 4. Okay. And then what's E? 1 go to 2. Okay. Then 1, 2. 2 go to 3, 2, 3, 3, 4, okay, 3, 4, and then 4, 1. Okay, there's no arrow, right? So this 4, 1, I can call it 1, 4. This 2, 3, I can call it 3, 2. It doesn't matter. Now, the middle one, I have this. Okay, now I want to call 1, 2, 3, 4, 5. Let's say I call it like this. It doesn't matter how you call it another way. Then my V is 1, 2, 3, 4, 5. Okay, what's the E? It will be 1, 5, 2, 5, 3, 5, 4, 5. Okay. 1, 5, 2, 5, 3, 5, 4, 5. Yeah. Lastly, this one. This one, normally you call it 1, 2, 3, 4, right? Okay. Then you call it like this. Then what is the V? 1, 2, 4. Okay. What's the E? 1, 2, 2, 3, 3, 4. So 1, 2, 2, 3, 3, 4. That's it. Now, another exercise. Now we have arrow. What's this V? I call it 1, 2, 3, 4. Okay, you may ask, why do I label it like this? Do I just make it arbitrary? Partly yes, partly no. Now I'm telling you, if you see a graph that looks like this, you should try make the node that go to the other one, that means the one that enter the other one, smaller number than the later one. This is like ordering. So it's like 1 go to 2, so 1 is before 2. 1 go to 3, it's like 1 is before 3. 3 go to 4, it's like 3 is before 4. Something like that. Of course, you can say, I don't care, I draw it in any order. You can. But if you do some algorithm with crazy naming, you will have disadvantage. So that's why I do it like this. So in this case, I will have 1, 2, 1 go to 2, right? And then 1 go to 3. So 1, 3, and then 2 go to 4. So 2, 4, and lastly 3, 4. Okay, V is 1, 2, 3, 4. Okay. Now this one, I will call this guy 1, and then 2, 3, 4, 5. Then I have a 1, 2, 1, 3, 1, 4, 1, 5. Okay. And V is 1, 2, 3, 4, 5. Okay. Lastly, this one, you should call this 1, 2, 3, 4. Then I have 1, 2, 2, 3, 3, 4. That's it. Okay. They have arrow. Okay. So these are the example. Okay. You need to practice. So now, in your spare time, do the same thing on this 31 graph. And let me tell you, this part we don't do in exam, and this part we also don't do in exam. I just let you know the thing exists. Okay. Suppose I have the graph like this, 3, 5, and 3, 5. We have 2 lines. Can we have some way to tell which is which? The answer is you grow a brother. So 3, now I grow a brother. So 3 become 3A and 3B. Why? Because I call this A and I call the thing B. So the lower one touch the B, so I make the lower one call B. The upper one touch A, so I call it 3A. So now I grow a brother. So now I have 2 nodes here. Then what? We don't care about how we name things. Call this 3B as 4. Then without the A, then this is what? This is 4. And then this is 4. Right? So that means what? That means now we suddenly create some new node and we no longer have what? Multiple edge. None of the ij repeat. Okay, and then here's another one. Suppose I have this 3, 4, 3, 4 or 3, 4, 4, 3. I can do the same thing. I duplicate a 3 to 2, and then I call this 5. Okay, then I have another thing. Okay, so therefore, with this trick, now if you look at this picture, 3, 5 have 2 edges. Using this, and I call this not 4 but 6, then now I have this 3 go to 6. Okay, this line is this line. Okay, but I duplicate a 3. So that's why this 6 and 3 have to connect each other. Now for the 3, 4, I also have 2 duplicated lines. Now this green line is this green line. So basically here, I just write a part of the graph and then do this duplication. Now I have this. So now I have this graph. You see none of the ij repeat each other. So this is how you convert multi-graph to simple graph. Then what about convert directed graph to undirected graph? You do the same thing. So here's another thing. Okay, so I have this incident matrix M. This means what? 1 do not go to 1, 1 go to 2, 1 do not go to 3. What does it mean? It means 2 go to 1, 2 do not go to 2, 2 go to 3. This means 3 go to 1, 3 do not go to 2, 3 go to 3. So I have this. I call it X, Y, Z. Okay, and these are all the meaning. I draw this graph. They are arrow. The next few slides is insane. I'm telling you, these two graphs are the same thing. Oh my gosh, what the heck is this? So this is why we will not touch die graph. This x go to y is the same as between x and y, I grow this crazy structure. So you can imagine I grow something that looks like this. Okay, I grow something like this. What the heck? I grow something like this. Then the idea is, if I give you this with the arrow, you can tell, yeah, this is x go to y and y go to x because x, y touch each other. But suppose, imagine, I give you this graph and I cover all the x, y, z. I don't tell you which is which. Can you tell which is x, which is y, which is z? The idea of growing this funny shape is to let you do that. Let's say you want to know, is this y? You look at the neighbor, which is called adjacency node, which is this guy, and you look at the degree. This guy, the degree is 3 because it touches 3 things. Okay, and then if you look at this guy, what's the adjacency neighbor? This guy. This guy, the degree is also 3. So these two nodes both have degree 3, and let me call it 3. I put 3 here. But what's next is important. This guy is the neighbor of this degree 3 node. This guy, the degree is 1 because only touch 1. But this guy, the degree is 2. It touch 2. So the idea is you create this shape so that you have 2 new nodes, both are degree 3. So in here, how do you tell which is x, which is y, which is z? You first find those nodes that are degree 3, which is this one, degree 3, right? This one, also degree 3. Then you look at these 2 nodes, the neighbor, and talk about their degree. This guy is degree 1. This guy is degree 2. You use this 1 and 2 to differentiate which is x, which is y. And that's why this is how you convert a digraph to a digraph. Okay, finish. Not in exam. I just let you know this kind of thing exists. That's it. So this two part, no. Okay. Then for simple undigraph, there are 2 extreme cases. In set, the simplest set is nothing set. In graph, the simplest graph is null graph. That means it's empty set. Empty in the sense of what? Of the edge set. And then we also have what? In math, we have infinity. That means a biggest number. In graph, we also have infinity, which we call it complete. That means the biggest possible way you can complete everything. So this is a null graph. So here I have 4 nodes. 1, 2, 3, 4, 5, 6. Okay, I forgot to draw 2 nodes. Okay, and then E is empty set. That means no edge. So the number of edge here is 0. What about the degree, adjacency, and incidence? All 0 because they don't touch each other. And null graph basically means empty set. What about complete graph? Complete graph means if I have a bunch of nodes, you draw all the possible lines as you can. So I have 1, 2, 3, 4. So I have this. Again, I don't care how you order them, how you name them, doesn't matter. So this is 1, 2, 3, 4. And then what? How many nodes? 4 nodes. 1, 2, 3, 4, right? What are the edge? You think of all the possible ij. These are all the possible ij. Okay? How many edge? Now we see combinatorics. It will be V size of V choose 2. What does it mean? It means I have 4 nodes. I randomly pick 2. How many way can I pick? I have 4 nodes, right? 4 choose 2. So this is number of edge. Now you see why graph theory is after combinatorics. Okay? And this is what? This is the complete graph. Let me tell you, this is also a complete graph. And let me tell you, they're the same thing. Imagine this is 3-dimensional space, and then you stand here, look into this angle. Okay, this is you, this is a human. Then you see this, you look at this sharp point, this is a pyramid, then you see something like this. That's why they're the same. So you can think of two graphs the same is like something 3D rotate in 3D. Actually, it's not just 3D, it can be 4D, 5D, 6D, whatever D. So this is why it's hard to tell whether or not two graphs are the same. Because I can give you two graphs, actually they're the same, but if you have 4D vision or 5D vision, you can tell. But human only have 3D, that's why we cannot tell. And what is the M and A? Again, we don't talk about linear algebra, so you don't really need to worry about too much about this. But degree, you need to know. Everybody touch 3. This guy touch how many points? 1, 2, 3. This guy touch how many points? 1, 2, 3. That's it. And complete graph, we use letter K, and then summary. So VVEMAD, direct graph, undirected graph, arrow, no arrow. Do you allow multiple edge? We don't allow. Do you allow loop? We don't allow. Simple means no loop, no multi-edge. Okay? This one is insane, no worry. This one is also insane, no worry. So that's why I said no in exam. So basically what? You need to know how to write the graph as I said. And now we will focus on simple undigraph. Okay? So first we talk about subgraph. It's like subset. So subgraph is what? You have subset, right? Then I will call it S. Subset starts with letter S. Then we just use the concept subset. U is a subset of V and F is a subset of E, and that's it. So this is a picture example. This is a graph, and then if I only look at this part, this is also a graph, and this is a subgraph of this guy. So here's an example. Suppose I have a graph like this. I'm going to ask you how many triangles are there in this graph. So how do you solve this? Lecture 1, if you don't know how to solve, always do brute force. This is exactly brute force. So you really just try to think about all the triangle here. And then this is the first triangle, this is the second triangle, this is the third, this is the fourth, this is the fifth, the last one. Important, this is a triangle, but this triangle has more than 3 nooks. I'm talking about what? Triangle graph, that means you have 3 nooks. So this graph has 6 triangles here. Then very naturally, you will ask, is there a way to systematically count how many triangles in a graph? The answer is yes. All the things you learn in combinatorics carry over here.